So in this chapter, we are going to introduce chapter 4, the molecules and compounds. We're going to talk about how we write them, what those formulas mean, their structure. We're going to talk about how to draw their structure, everything about compounds and molecules. So when two elements come together, they form a molecule. And we can see that, for example, the oxygen in O2, remember oxygen is a diatom, that oxygen can bond to itself. It can also bond to hydrogens. It can bond to metals like magnesium. And it can bond all sorts of different ways. When it bonds to sodium, right? There's all different ways that an individual element can combine. But when it's combined with a particular element, all the molecules of that element are the same. So every single water molecule in the universe is an oxygen bonded to two hydrogens. Molecules are compounds. So if you look at water and we say, okay, so we have H2, that hydrogen makes up water, O2, oxygen makes up water, and then when they come together to form water, you can see the characteristics of all three change dramatically. Hydrogen just by itself has a boiling point of negative 250 degrees, 53 degrees Celsius. Water's freezing point is 0 degrees Celsius. So you can see that there's a huge difference in boiling points of these two compounds. And so that characteristic changes as soon as a hydrogen and oxygen come together. At room temperature, hydrogen and oxygen are going to be in their gas form, where water is going to be in the liquid form. And that all is going to have to do with the sharing of electrons that these elements have, and how they behave is directly related to what they are bonded to and the shape that they form. And we'll get into all that. So a hydrogen-oxygen mixture can have any proportions, but in water specifically, it is a 2-to-1 ratio. But we can also have peroxide, H2O2, okay? The point is, the hydrogen and oxygen can come together and form many different things. It can form a hydroxyl group, which is the characteristic that makes something an alcohol, like ethanol or methanol, okay? It's that OH group there. But water in particular is always two hydrogens, one oxygen. So the types of chemical bonds we're going to be talking about, we're going to be talking about ionic, covalent, metallic. So ionic bonds are between metals and nonmetals. Covalent are between all nonmetals, two or more. And metallic you would see as attractions between individual metals attracted to their own individual atoms. So like for example, gold in its solid state, which is how it naturally occurs in nature. The attraction between the gold molecules is a metallic bond. So here's an example of ionic bonding, metal and nonmetal, the sodium chloride. In ionic bonding, the metal gets a full charge in and of its own right, as does the nonmetal, as opposed to a partial positive or partial negative charge, which we're going to see in covalent bonding. Okay, all nonmetals, ice, for example, water, CO2, carbon monoxide, etc., etc. So the way that the ionic bonds get their full-on charge is because they transfer electrons from one to the other, as opposed to a sharing of the electrons. So when ionic bonds come together, a metal it's always the metal, gives up the electron, and therefore it becomes positively charged, and we call that a cation. Nonmetals always take those electrons, they gain those electrons, we call them anions, and they become negatively charged. So when we look and see what happens here, if I just have a regular old ordinary neutral sodium right there and a neutral chlorine, as soon as that sodium gives up an electron and becomes an ion, it is now going to be attracted to the negatively charged chlorine, which is now a chloride ion that has taken that electron. And because they're opposites attract, that's what brings them together. Covalent bonds between our nonmetals are a sharing of electrons. This can be an equal sharing, and we're going to call that nonpolar, or it can be an unequal sharing, and we're going to call that polar. Okay, so think of it this way. If I have my exact clone and I'm playing tug of war with it, we're both holding the same rope, sharing the same electrons, but that red flag is going to stay even between the two of us. The electrons are going to be evenly distributed between us. But if I'm me and I'm playing tug of war with a 3-year-old and I'm mean and I want to win, we're still going to be holding that same rope, but the red flag is going to be much closer to me. I'm much stronger and I have much more energy, so I can pull what's being shared closer to me. The same would happen with unequal sharing of electrons. One thing is going to be stronger than the other, so they're still going to share electrons, but the stronger one is going to be holding them much more closer to itself. Okay. When we have covalently bound atoms that compose a molecule, we get molecular compounds. That's what we call it. So we use a chemical formula to represent our compounds. This is going to be the symbol of the element, and then there's going to be subscripts, which indicate the number of how many of that element there is. And then sometimes we'll be using parentheses. You'll see why when we get to talking about the polyatomics. Okay, so here, this is what we mean. This is a chemical formula. Okay. What this chemical formula that I just wrote tells me is that there are 2 irons and 3 oxygens. We know what element it is, and we know how many of each one there are. Okay? Empirical formulas, molecular formulas, and structural formulas. All this means is that the empirical I kind of think of as like the parent formula. It's the formula from which the molecular formula can grow off of. Okay? The molecular formula is going to be a multiplier of the empirical. All right? And then the structural formula, that's just a letter and stick model where I'll show you an example of those. So empirical formula, again, it gives you the smallest, simplest whole number ratio formula that's possible. From that, we can grow an empirical. So if I look at C4H8, for example, I can see that with the 4 and the 8, just like when we reduce fractions, that's not the lowest whole number ratio I could get. I could divide both of these by 4 and say, okay, CH2 is my empirical. Okay, so if that's my empirical, then the molecular is going to be some multiplier of that. In this case, it was CH2 4 to get the molecular, and then the 4 is distributed. So I could say C4H8, I could say C2H4, I could say C6H, what did I say, 6? 12, okay? So these are just multipliers of the empirical. Our structural formula is like this. It tells us what's bonded to what. When we see this formula, we're going to have to figure out, well, what's bonded to what? Um, and the structural formula shows us where everything is. Okay, so if I have just some chain, some R chain, doesn't matter what it is, and I'm looking at this, I can say, all right, I have one oxygen double bonded to the carbon and a hydrogen bonded to the carbon, and not the oxygen bonded to the carbon, and the hydrogen is bonded to the oxygen. Okay, so these are just structural formulas that tell us where everything is in the structure, and we're going to learn how to do that. I do recommend going through and doing these. Okay, um, so this is just the summary of the types of formulas that we have. Go ahead and review this and practice with it. So I do recommend, especially if you're going on to organic chemistry or you need to go on to organic chemistry, I highly recommend just going to Amazon. They're less than $20. Go ahead and buy you a molecular model kit. Um, they're pretty compact. They come with their own, all the stuff that you need, and you can build your own models. You're gonna need that's gonna be extremely helpful in organic, but it will also be helpful in here. Okay, we call these, or these are technically the ones you buy on Amazon. They're less than 20 bucks. A ball and stick molecular model kit, because you have the balls that are different colors that represent the different elements, and then the sticks kind of go so they can connect together, and you can literally build your own compound. So this is what it would look like with a molecular model kit. This is in real world what these atoms actually look like, because when we just write a hydrogen, what we really mean is that there's what we call an electron density surrounding that hydrogen. It's not just a H put up there. It's a ball. It's an element, and that's how we represent it in ball and stick. But really, it's got this whole electron density, or more like an electron cloud surrounding it. So all these clouds kind of intermix. But I'm never going to attempt to do the space filling model. It's just ridiculous. I go about as far as this right here for how we draw, but we're going to learn how to draw the compounds in a later lecture. So this is just, again, a summary of the different ways that we can write different things about a compound. Obviously, the name, there's going to be, in here, we'll focus on the IUPAC system of naming. When you get to organic, you will need that, as well as what I refer to as the common name or the street name. So here we can just write the empirical formula, molecular formula. Here's one structural formula, another structural formula, space filling formula. Um, so again, it's just when you can build it, like if you draw this on a piece of paper, two-dimensionally, you cannot see that this compound actually takes on this kind of shape. You can kind of see it here, but not the same, okay? So we're going to do Lewis dot structure in the next lecture, and that will be a part 2.